So my plan for today is I'm going to work through some more questions from the practice exam. I'm also completely happy to take questions from you about any topic or anything you want me to go into more detail about. This and the office hour after this is the last chance you have to ask me stuff before the actual exam, which is, as you know, this afternoon. All right, so good. Let's get going then. So we have question 2, and it is apply the integral test to determine the convergence or divergence of this series. That's part A. And part B, write down the fourth partial sum. And then part C, use integral test to determine an upper bound for the error. So in other words, to determine how close S4, the first 4 terms, are to the actual answer. Okay. Solution. All right, so we have a series of positive terms here. So let's start by drawing a picture. So we think of them as being the area underneath these blocks, as always. Okay. And we have to use the integral test to show it converges. We're pretty sure it converges anyway, right? We know that these terms are going to 0 incredibly fast, but doing as the question asks, let's use the integral test. So we need to find a function that recovers the terms of this series. So draw them here. Let's put a 1 here. This is a 2. This is a 3. This is a 4, and so on. So we need a function. F such that f of n is n e to the minus n squared, and it should be not hard to come up with that for you people. You just do this, and then you notice when you put n in this, you get exactly what you want. Right? So if we draw a picture to visualize this, then our function does this, right? Our function does this. Yeah? So when we're at 1, this is where f1 is. When we're at 2, we're at f2. This thing is exactly represented by the dots I'm drawing here, right? That's the meaning of the thing, is the dots I'm drawing here. Cool. So we see from this picture and from this general principle that the thing will converge if the area underneath the graph of this function that recovers the terms of the series is finite. In other words, it's a proper integral of type 1 converges. And that's something we can just calculate. So let's just do that. So we can start at any particular point. It doesn't matter. We can start at 5, at 7, at 1. Anything that works and converges will mean that the entire series is converging. Let's just start for 1 in this case. So we have 1 to infinity. And we're going to integrate f, so it's x e to the minus x squared dx. And this is an easy integral. This is a u sub. We get u equals x squared. Du equals 2 x dx. So we have du over 2 equals x dx. We have this x dx structure here. So this thing, call this thing star. Star is equal to the limit. If you're doing this in free response, you absolutely have to write these with the limits as r goes to infinity. You will be judged very harshly if you do not do that. Right? We've taught you how to do improper integrals, and you need to do this carefully. And now we can turn this into an integral in terms of u. So we substitute the limits. So when x is equal to 1, then u is also equal to 1. So with this, when x is equal to r, then u is equal to r squared. And then we are going to have this 1 over 2 right here, and then it's e to the minus u du, and then that's an easy thing to integrate. And 1 over 2, 1 to r minus e to the minus u. and that's the limit as r goes to infinity, 1 over 2 minus, oops, r squared minus minus 1. So it's equal to e to the minus 1 over 2, and therefore the integral converges. We need to also, just to nail everything down, we need to also make sure that this is a continuous function that's decreasing. Yeah? So f of x is clearly continuous because it's the product of continuous functions. And we need to check it's decreasing. So that thing, we actually do need to do a little calculation. I mean, it should be sort of fairly clear to you it will be, because this e to the x squared is increasing so much faster than x that it will be actually going down. It will be a decreasing function, but let's check it. So we calculate the derivative of this, f prime of x. So I'm going to think of this as x over e to the x squared. So we put everything under the bottom guy squared, differentiate the top guy, leave the bottom guy alone, minus, leave the top guy alone, oops, differentiate the top guy, leave the top guy alone, differentiate the bottom guy, so we're going to have, so we're differentiating the x squared, so we're going to have 2x e to the x squared, like this. And what's this? Let's pull out the x squared. So we have x squared 1 minus 2x squared over x squared squared. And sure enough, this is less than 0 for any x bigger than 1, so it's a decreasing function. All right, so we have definitely shown that this thing converges by the integral test. Yeah? We've checked the conditions, it's continuous, the derivative is negative, and the integral converges. Yeah? Everybody happy? Cool, so that's part A done. Part B, write down what S4 is. Well, okay, that's just the sum from n equals 1 to 4 of this thing, the first 4 terms. And part C is find how close as... All right, cool. Everybody good? Any other questions? All right, so this is S4, and then the final part of this is to use the integral test to determine the error between S4 and the actual answer. So let's call this thing S, actual sum itself. And this requires using the integral theorem error estimate. And we've talked about this a number of times. I want you to draw the picture and then get the correct thing just by reading off what the picture tells you. I don't want you to memorize indices or anything like this. So what is S4? It's the first 4 terms. So it's these guys here. I'm going to outline in blue. So the difference between the first 4 terms and the actual answers is all the other blocks, which are these guys here, which I'm doing in red. So to get an upper bound on how far the first 4 blocks are to the actual answer, it's going to be just the area. Well, let me say that again. The difference between the first 4 blocks and the actual answer is just the area of all the other blocks. So this one, this one, this one, this one, right? And an upper bound for that, as you can see, is just integrating the function from 4 onwards, because the area of all these red blocks is less than the integral of our function from 4 onwards. Yeah? Yeah? Give me a thumbs up if that makes sense to you. I claim if you draw this picture, there's no way to get this wrong. So I do want you to draw this picture. Cool. So, because this is the most common thing to actually get wrong, actually. So for part C, we know that R4, which is the remainder, which is the difference between the actual sum and the first 4 terms, and this is the sum from k, well, we used n, so from n equals 5 to infinity of all of these terms, n e to the minus n squared, is less than the integral from 4 to infinity of our function. Yeah? Cool. So that's the only thing we need to do, is to calculate this. And it is this calculation, except we are starting from 4 instead of from 1. So at this point here, this number here would be 4 instead of 1. So just using this, so let's take this up here. This is less than, I'll drop the limits. Oh, I erased limit signs here. So limit as r goes to infinity. This is less than the limit as r goes to infinity of 1 over 2 e to the minus r squared. And now this limit here, we have to be careful. We have to be careful because 1 as a neat translation when you do the substitution. So we're doing this from, let's replace all of these guys here. So we're doing this from 4. And now when we do the u sub, when x equals 4, then u is 4 squared, which is 16. So at this step here, we now have 16. And now we have 16. And now we have 16. Yeah. So all we're doing is just replacing the 1 with 4 in this calculation right here. Yeah. So to save board space and time, I'm just recycling it. So then this thing, okay, I've already put it in. This thing is this. So then the error is less than e to the minus 16 over 2. And that's the answer. Everybody okay? Yeah, everybody happy. Good. All right. That's another one. And the question is, which of the following are conditionally convergent? So this is the first one. This is the second one. Oops. Let's n to the 3. And this is the third one. Okay. Let's do a survey. Thumbs up if you think this is conditionally convergent. If I is conditionally convergent. Thumbs down if you think it's not. What condition are we also paying attention to know that this thing converges at all by the alternating series test? Right. Yeah, each term is less than the one before it, indeed. Yeah. So this 1 over n is a decreasing sequence going to 0. Yeah. If we just had positive terms, we know that thing doesn't converge. Yeah. But if we have minus 1 to the n, it's an alternating series that satisfies the conditions, this thing definitely does converge. So it doesn't converge absolutely, but it does converge, therefore converges conditionally. Again, this is the picture. This is the thing, the blob represents all things that converge. Converging absolutely is this, and converging conditionally are those which are not converging absolutely but still converge. So it's the outside, yeah? Because converging absolutely is a stronger condition. Okay, so this one I agree. All right, let's look at the second one. Thumbs up if you think it converges absolute. Start again. Thumbs up if you think it converges conditionally. Thumbs down if you think it doesn't. Okay. All right, so someone else tell me why this one doesn't converge conditionally. because it converges absolutely. We take the absolute value, it's just 1 over n to the 3. We know that converges. Just use the p-test, p is bigger than 3. Good. So this one does not converge absolutely. Next one. Thumbs up, you think this converges absolutely. Start again. Thumbs up, you think it converges conditionally. Thumbs down if you think it doesn't. All right. Someone else. Tell me why you think it converges conditionally. Come on. Excellent. Yeah, it's slower than 1 over n. Yeah. So by the so if we take the absolute value, so I'll consider 3. You can either point out this is going to 0 slower than 1 over n, or you could just say by the p-test, since p here is a half, does not converge. So it's definitely not converging absolutely, but it is converging because, again, by the alternating series test, this is these terms, 1 over square root of n, they are going down to 0, and they are decreasing one term after the other. Yeah, they are monotonically decreasing. So it does converge, but doesn't converge absolutely. Good. All right. So that one was kind of straightforward, huh? Some of these practice questions are kind of logic questions, not logic questions, but kind of conceptual questions, testing rather carefully what you know to be true or not true. So, well, I mean, I don't think that they are hard questions, but you have to know, you have to understand these concepts. So this is question 13. Suppose we have this series, and this series converges. And they have positive terms. And we have that an is less than bn. Then we have a bunch of statements. We have to determine the one which is not always true. So is this, that if the sum n equals 1 to infinity bn is convergent, this implies the sum n equals 1 to infinity an plus bn is convergent. So given the information we have here, is this always true? Thumbs up if you think yes. Thumbs down if you think no. I see lots of thumbs up. Good. Someone quickly give me a reason as I write the next statement. Someone hasn't spoken yet. Yep. Yes. So if B and N converges, A of N also converges. Can you add some more to that? That's all good. But this is not either B of N or A of N. It's the sum of the two. So why do we know that this guy converges? You're almost there. Yeah. Yep. So this is this general fact that I told you, that whenever a series converges, you can treat it just like a finite sum. All the algebraic rules that are true for a finite sum are true for a series, right? So this series right here, the series of an plus bn, it's equal to the series an plus the series bn. Right? This is one of our theorems that we learned. And this just comes down to the limit laws. Yeah. So exactly as the first guy said, since we know that this converges and this converges, yeah, then we know that this thing converges because of these limit laws, and it's equal to the sum of these two guys. Okay. Okay. Perfect. Another way is to say that this thing is bounded by 2 times bn. Yeah. So an plus bn is bounded by 2 times bn, right? So by the comparison test, since these are all positive terms, then this thing must also converge. Yeah, that would be another justification. Okay, cool. Look at statement 2. Thumbs up if you think that's always true. Thumbs down if you think it's not. Okay, everybody says things up. Everybody thinks thumbs up. Someone give me a reason. Come on. Perfect, yes. That's completely correct. Yes, yes. So by the divergence test, unless we have that these terms go down to 0, there's no way it can possibly converge, right? Yeah. So since Bn is convergent, An is convergent, therefore both the limit of n goes to infinity Bn is 0 and limit of A goes to infinity goes to 0. Yeah. Yeah. Or you could say, since this is convergent, then this has to be true, right? But An is trapped between 0 and Bn, so by the squeeze theorem, we also know that An has to go to 0. That's another way. Yeah? Cool. You people are doing very good. All right. Next statement. If sum n equals 1 to infinity, Bn is convergent, this implies both the sum n equals 1 to infinity minus 1 to the n, An is convergent, and the sum n equals 1 to infinity minus 1 to the n, Bn is convergent. Thumbs up if you think that's true. Thumbs down if you think it isn't. All right, someone new still hasn't spoken yet. Give me a reason why. So most of you think that this is always true. Give me a reason why. I see what you're saying, but so what you're applying is the alternating series test. But do we have all the conditions to apply the alternating series test? Do we have all the conditions? What are the conditions? Each term has to be smaller than the last one, right? And under these hypotheses, with these assumptions, do we know that each term is less than the previous one in this case? No, it's not possible to infer, and it's not true. Yeah, it's just not true. We could have a series where every now and again we have a term which is bigger than the previous one, then it isn't going to matter. Let me come up with an example. Yeah, all right, what if we do this? What if we have a series where a to the 2n was 1 over 2n squared, and and a to the 2n plus 1 was say 5 over 2n squared. Yeah? So this series of terms, this guy is the next one from this one, right? But it's not smaller, it's actually bigger. Yeah? It's actually bigger. So this series of terms we have an even number like this, the next guy is up, and then we're down, the next guy is up, we're down, the next guy is up. Yeah? But this series, defined like this, will still converge. So in pictures, look at this. So suppose we have a series where we have a term like this, positive, the next one is a little bit higher, and then we go down, the next one's a little bit higher, then we go down, the next one's a little bit higher. Then we're still going to have that the area underneath this thing will be finite. But it doesn't have to be monotonically increasing. Yeah? So converging does not mean it's monotonically decreasing. Yeah? So it's very natural to apply the alternating series test, and thank you very much to the person who suggested that. But that's not the reason. That's not the reason we can conclude that this is always true. So think what else we know about series. How else do we show that series that don't necessarily have positive terms converge? What other tool do we have? How else did we ever do it? Right. Indeed. Yes. Yes, exactly. So we have this other fact that we used, that if something converges absolutely, then it converges, right? Yeah? Remember that? So let me write it down. So if sum, let's call it something else, if the sum Cn converges absolutely, then it converges. And that was this picture, right? So converging absolutely is a subset of things that converge, right? It's a stronger property. Yeah? And if we look at this term, this series right here, let's start actually with the Bn. If we look at this series right here, then if we just ignore the alternating -1 to the n stuff, then just take the absolute value of this series, we just have the series Bn. We just have the series Bn, yeah? And the series Bn does converge. So this thing converges absolutely, therefore it converges. Yeah? Thumbs up if you're with me here. This is important because you might have some question where they're asking you why. Yeah? Thumbs down if that's still not clear to you. Okay. So, once again, this thing converges absolutely because it's just the series Bn, which by hypothesis we know converges, so therefore it must converge itself. Yeah? Same for this. Because these terms An are less than Bn, then An also converges absolutely, therefore this thing also converges. Yeah? So we have two ways to deal with series that have positive and negative terms. Either it's an alternating series, we can check the conditions, the terms in front of the -1 to the n are going down to 0 and they're monotonically decreasing, or we can show that the series is absolutely converging. So remember when we had things like this, we had like cosine of n to the n squared, or n to the 3 have I just written, yeah? Then there's no way to apply the alternating series test to this, right? Because it's not alternating, yeah? But we can still show it converges because we know that this thing converges absolutely because cosine absolute value is between 0 and 1, yeah? So the absolute value of this is less than 1 over n to the 3, so by the comparison test, the absolute value converges, therefore it converges. Remember this, huh? Yeah? Cool. So keep this in mind. There are two things. There's the alternating series test, or there's showing something converges because we can show it converges absolutely. Those are the two ways we can deal with things that have positive and negative signs so far in this course. Yeah? In this case, we have to use the second thing. We have to use that it converges absolutely, therefore it converges. So this is a bit more of a subtle one. Yeah? But we can still answer it with what we know. Cool. The final, not the final thing, another thing. This is D. I'm running out of space. Okay, I'm going to clean the board. I will say it out loud and you think about it. So D is, if the sum of An diverges, then the sum, start again. If the series An diverges, then the series given by An plus Bn diverges. Is that always true? And if that's always true, yes, I mean, I see what you're saying. Can we use some principles that we've learned? I still see what you're saying, but let's put it in terms of the principles that we've learned. Your intuition, your picture is exactly right, but we have these basic principles we use over and over. What principle are you using implicitly there? Let's draw a picture. So these are An. Yeah? They diverge. The area underneath these guys, when we add them all together to infinity, is infinite, right? And if I'm going to draw the Bn, start again. If I'm drawing the An plus Bn, what am I going to draw? What's it going to look like? It's going to be these blocks that are above, right? Yeah? That's what the AN plus BN will look like. Yeah? These are the AN. This is A1, A2, A3, and so on. And these guys is A1 plus B1, AN, A1 plus B1, and so on. A4 plus B4, and so on, right? And we know that the area underneath the blocks given by the AN diverges. So why, using the principles, what principle are we using here? Why do we know that the series AN plus BN diverges? Yes, it's the comparison test. Because AN plus BN is definitely bigger than just AN, you know? Implicit in what you were saying was the comparison test, that if you have something that diverges and you add something on top of it, then of course it's going to continue to diverge. Agreed, yeah. But just stating it in the terms of the principles we've learned, you're implicitly saying that if you add something on top of it, then it's bigger. No? And if it's bigger for every single term and we take the series, then it's going to diverge. No? And this is a little bit important because, again, if it's a free response, your examiner will want you to phrase things in terms of principles that we've learned. Yeah? So you can have the right idea, and the people who answered did have the right idea, and I think the right picture, but we've codified these reasons with these standardized principles that we use, and these are the actual. This is the most of these are actually what you're using, whether or not you explicitly say it. And it's just going to be better for you to say it in terms of stuff we are used to reading as the reasons. Huh? So don't implicitly use a principle. State it explicitly. State explicitly what you're using and what you're using as a comparison test. Comparison test. Everybody clear on this? Huh? Thumbs up if everybody's happy with the distinction. All right, cool. Final thing. This is E. If the limit as n goes to infinity an is equal to 0, then some infinity an converges. Is this always true? Thumbs up if yes, thumbs down if no. Seeing lots of thumbs down. Someone who hasn't spoken yet, tell me why. Tell me why. Again, I appreciate it takes some courage to tell me why, particularly if you don't get it right, but you're helping everybody. You're helping me, you're helping everyone else who's listening. So go ahead. Yeah, well, what I think you're saying is that just because the limit is 0 doesn't mean it has to converge, right? Because when you have a series of positive, it's not the comparison test. It's just the stuff that we've been learning there. The terms, if we have positive terms, they have to go to 0 fast enough, otherwise it won't converge, right? Can you think of an example where that doesn't happen? Can you give an example of a series of positive terms that go to 0, but at 1 over n, yeah? Consider right? This is the classic example of a series whose terms go down to 0, but they're not going to 0 fast enough, therefore it doesn't converge, right? So if we have positive terms, they have to go to 0 fast enough. If it's an alternating series, we don't care. They just have to alternate and be monotonically decreasing going down to 0. Yeah? Cool, so not always true. Okay, you people seem to be in good shape for this kind of stuff. All right, question 14 is a similar kind of question. the first thing is exactly the same thing. Let's do I. And the statement is, the question is, which of the following are true for any series of positive terms? So an are positive terms. So if we have that the limit as n goes to infinity of an over 1 over n equals 1, then this implies that the sum from n equals 1 to infinity an diverges. Thumbs up if you think this is true. Thumbs down if you think it's not. We have a lot of abstentions and then a mixture of thumbs up and thumbs down. Come on, have courage. Let me know what you're thinking. Thumbs up if you think it's true. Thumbs down if you think it's not. All right, someone who thinks it's true, tell me why. That's, I like, yeah, I see what you're saying. So a lot of your answers are kind of encouraging because you're thinking about this in the right way, or you're roughly speaking the right way, but not quite precise enough. This isn't an equality; it's a limit. It's a limit. So we can't do this, but we can almost do this. That's what a limit means. So your intuition is right, and I like the intuition. That's completely good. But we can't quite do this. We can't just try and solve this for an and say that this is like that an is like 1 over n. But there's a principle underneath this which allows us to actually do this in a general context. What principle? What principle is underneath this? Indeed, that's it. Indeed. What principle have you used then? The limit comparison test. Yeah. Implicitly, the first person who answered was using the limit comparison test, and in a completely reasonable. I mean, I completely understand why you thought that and why you said that, and that's completely the right intuition. This exactly says that an is more and more like 1 over n, and when I explained the limit comparison test, I said, okay, well, if we think about it, then these blocks are all comparable. They're all. This thing would say if this is 1 over n, then after a while, then an is less than 101% of 1 over n and bigger than 99%. It'll be trapped very, very close to it, right? So then we'd know that an is somewhere between here and here, right? Between 1.01 and 0.9 of an, and therefore, for sure, it's got to do whatever an does, whatever 1 over n does. So, yeah, but we have a machine to do that, and that's the limit comparison test. So, limit comparison test. And in fact, the limit comparison is exactly this condition. It says that an is married to bn. So whatever one does, the other one does, right? You diverge, you converge together. No? So therefore, this is always true. Therefore, this is always true. So I like this one, which this one, this statement here. Okay. Because this isn't a ratio of an to anything else. This is just saying that this thing tends to 0. Whereas this thing is saying in a more precise way, right? So look, if we consider what the limit means, right? So this is 1 over here. And this having limit 1 means that if we go a little bit higher, say 1.0, let's just do 1.1, and a little bit lower, say 0.9, then we are trapped in between this strip with our terms like this. So these things are an over 1 over n. Yeah? So after a while, they're always trapped between this thing. So that means that 0.9 is less than an 1 over n is less than 1.1, right? So in particular, let's put it over here. We have 0.9, 1 over n is less than an is less than 1.01 over n. So then, since this thing is diverging and this guy is underneath it, it diverges. So they're completely locked into each other when we have a relation like this. And in terms of pictures, it means these blocks are really, really close to each other. This thing is much weaker. This thing is saying it's going down to 0, but it's not saying in any way, right? Whereas this thing is saying in a really precise way, we're going down to 0. We're going to 0 really, really a lot like 1 over n. Yeah? So they're both limits, but this is a lot stronger information. If instead of having this, we had 1 over n squared, then we'd end up with this relationship. Yeah? So we're tending to 0 like 1 over n squared, which means it will converge because it's less than 1.01 over n squared, which is going down to 0 fast enough. No? So, yeah. Thank you for the question. And so here's the question. They're both limits, but this thing, even though it looks formally a lot like this thing, contains a lot more information. It's a lot stronger. Cool. All right. So this guy is always true. So this is always true. And it's a kind of tricky question because you have to think for a little bit. All right. Next statement. If the limit as n goes to infinity of an plus 1 over an equals 1, this implies that a series converges. Okay, thumbs up if you think that's true, thumbs down if you think it's not. Oh, we're over time, I'm sorry. Leave whenever you need to. Okay, we have thumbs down. Somebody tell me why. Okay, I see what you're saying. Well, let's try and be precise. So let's look at this. Is it the case that each term is less than the one before? Yeah. So being less than the one before isn't enough, right? Yeah. Yeah. This is right. Yeah. This is a particular case of the ratio test where we actually don't know anything because this ratio being 1 doesn't tell us any good information. So if we look at an, then an plus 1 over an is just n over n plus 1, right? And that has limit 1. And bn plus 1 over bn, this is an example we did at the time, is n squared over n plus 1 squared. Again, the limit will be 1. Yeah? So this thing doesn't tell us anything. So when I told you about the ratio test, I said this is like an X-ray machine that will tell you if the series in its bones looks like a geometric series or goes down to 0 faster than the geometric series. But that's all it will do. And I said it's like an X-ray machine because it's only detecting some specific structure underneath it. Just like if you were going to the doctor and you had an X-ray and the X-ray was fine, it doesn't mean that there's other stuff not going on. It's just telling you about one specific thing, just the bones of how the series is going to 0 when you think about it in terms of, is it comparable to a geometric series? Yeah? You can have an X-ray and you're fine, but you have, I don't know, lung cancer or something. And, oh no, that would show up. Okay, you could have a brain tumor or something, and then you wouldn't know anything about it. So this is not something that is of any use unless you're in that context of something which is in its bones going down to 0 like a geometric series or faster. So by itself, it doesn't tell you necessarily anything. Yeah? It doesn't tell you like anything. Right? So think of the metaphor as of the X-ray machine, and think of the fact that X-rays don't tell you everything about your health, right? You could have a neutral X-ray, doesn't show anything, doesn't necessarily mean you're fine or that you're ill. The X-ray is only for one specific thing. The ratio test is for one specific thing. These are examples for which we can't tell anything from this. So this is not always necessarily true. No, this is not always necessarily true. So not always true. We have this series. -1 to the n plus 1 over n to the 3 equals 1 minus, well, I don't need to do this. It's 1 over 2 to the 3 plus 1 over 3 to the 3 and so on, minus and so on and so on. And the question is, does the series converge and why? And the second thing is, how many terms do you need to approximate it within 0.01? So terms. Okay. Firstly, does this thing converge? Well, the fact that we have this part 2, clearly we expect it to converge, right? Otherwise part 2 would make no sense. All right, why does it converge? Okay. All we need is that these guys, so this is of the form n equals 1 to infinity. So you're right, it does converge absolutely, but, I see what you're saying. So actually we could just say that it converges because it converges absolutely. So yeah, that's also a possibility. Or we could use the fact that it satisfies the conditions of the alternating series test, right? So this thing, let's write this like this. This thing where Bn is 1 over n to the 3. These are definitely decreasing, right, as n increases, and they're going down to 0, satisfies the conditions of the alternating series test, so this thing converges. Yeah? So converges by alt series test. Or notice that it converges absolutely. Okay, all right, second part. We need to estimate this within 0.01. So I have the alternating series test, which means that visualize the alternating series, we go forward by something, then backwards by something, and then forwards by something, and then backwards by something, and so on. Yeah? Yeah. And if this is where we are after doing n steps, so this is where we are after Sn, yeah? So that means this thing here is the step size Bn plus 1. Yeah? Then, going forward, what happens, well, if we keep going, what happens? We go backwards first by the next thing, which is step size Bn plus 1. So this is Bn plus 1. And then we're going to go forward by Bn plus 2, which is less than Bn plus 1. So we're not as far as where we were at the Sn step. And then we go backwards by Bn plus 2. We don't go as far back as we were. You know? And then we go forward, and we go backward, and so on. And we notice that we are trapped forevermore between here and here. Yeah? So, whatever the answer is after this infinite series of steps forwards and backwards, say this point here is the answer, Sn, then the distance between Sn and so again, if this is where we are after infinite number of steps, call it S. The difference between S and Sn is less than the Bn plus 1 step size. just from this picture. Yeah, just from this picture. So we just need to find n such that the bn plus 1 step size is less than this particular error. So let's write that down in words. So need, oops, to find n such that bn plus 1, need to get new pens, bn plus 1 is less than this error. So that is 1 over 100. That's all we need. Yeah? Okay, cool. So let's just look at these terms. So b1 is just 1. b2 is 1 over 8. Oops. b3 is 1 over 3 to the 3, so that's 27. b4 is 1 over 4 to the 3, so that's 16 times 4, which is 64. Yeah? And then b5 is 25 to the 3, so that's 25 times 5, which is 125. Like this. Yeah? So this step size is less than 1 over 100, right? Yeah? So if we do this thing, so we go forward by b1, then backwards by b2, then forwards by b3, then backwards by b4. That's the last step we need to take, because from then on, we go forward by b5, backwards, forwards, backwards, forwards, backwards. Wherever we are, its distance away from here is less than b5, which is 125, which is less than 1 over 100. Yeah? So we just need to stop here after doing 4 steps to actually get the answer to within actually 1 over 125, which is less than the error we need. If we stop after 3 steps, it's no good, because we can't guarantee that the difference between the actual answer and where we are after 3 steps is less than 100, less than 1 over 100, right? Because if we stopped here, then it could be that the actual answer is like somewhere over here, right? Yeah? You see what I mean? Yeah? Cool. So we just need the first 4 steps. So the question precisely is, how many terms I need to approximate within this thing? So we need 4 terms. And S4 is within 0.01 of answer of series. If you draw this picture a few times, you should be comfortable with this. You should start to believe or be convinced or feel confident that this is correct, that this is true, that if you take the first n terms and sum them, then the difference between the actual answer and the Sn partial sum is less than the Bn plus 1 step size. So just draw this for yourself a couple of times, convince yourself, and then you'll have confidence in applying this theorem. You'll get this right. Yeah? Cool. All right, I have always hour now. Stick around if you have any questions. Otherwise, good luck later today, and see you all on Wednesday. Bye-bye.